Welcome back, students. In this video segment, we will cover section 6.3, the natural exponential function. So let's go ahead and get started. In order to get started, what I'd like to do is to kind of remind us of what we did in the last section, because this lecture builds on it. I guess before I even do that, I should mention that this is section 6.3 star or asterisk in our textbook. Okay, so in our last section, we studied the logarithm function, the natural logarithm function. F of x equals the natural log of x, and we learned a whole bunch of stuff about it. In particular, though, we learned that it behaves just like the logarithms, because it is just like the logarithm, one of the logarithms that you studied in pre-calc. Its graph looks like this, and a real important aspect of the graph is that it grows extremely slowly. I didn't mention it this way in our last video segment, but you can illustrate that by saying that the natural log of a very large number is not so large. Is not very large. I'm going to put that in quotes because it kind of violates something about the natural logarithm, that the natural logarithm does get very large eventually. So we know that the limit of the natural logarithm function as x goes to infinity is in fact infinity. Okay, but if we're not looking at infinite values for x, the natural log of huge numbers is not that large. Okay, so this function grows very quickly. It levels off. That means the slopes approach zero, yet it doesn't have a horizontal asymptote, which is kind of mind-boggling. Okay, in this section we look at the natural exponential function, which is the inverse of the natural logarithm function. So what I'm going to do is I'm going to find the inverse of the natural logarithm function, just using some algebra. Then we're going to look at the graph and properties of the natural exponential function, and then we'll look at using some calculus involving this function, the natural exponential function. Most of the time, it's not referred to as the natural exponential function. It's just called the exponential function, even though there are many exponential functions. We see this one so often that very often it's just referred to the exponential function. And one other thing, and I'll show you what that is in a few minutes. Okay, so let's go ahead and find the inverse of the natural logarithm function. In order to do that, we have to remember that the natural logarithm function has a base. So if the function is the natural log of x, that means written in terms of a log with a base, it's log base e of x, where that e, the base of the natural logarithm, as we mentioned in the last video, is equal to 2.718281828, repeats again, I think 4, 6, and it goes on and on and on. And like the number pi, it's an irrational number. It goes on forever and ever and ever, and there's no repeating pattern. So how do we find the inverse of a function? There's two steps, remember? The first step is to switch x and y, and then the second step is to solve for the new y. So step one, let's switch x and y. Well, in order to switch x and y, we need a y to begin with. So we're going to replace f of x with y. Then we're going to switch x and y. Okay, that's the easy part of this. And when we solve for y in this, we are looking at the inverse. In order to solve for y, though, we need to remember the defining property of the logarithm function from pre-calc. So I'm going to switch to green here, and then I'm going to say recall from algebra. So we're taking kind of a side trip here. If x equals the logarithm base a of y, that means that a to the x equals y. That's how we define the logarithm in algebra classes. So for example, if I have 9, I don't think that'll work. Let's see. 2 equals, I'm making up a problem here, log base 3 of 9. This is true. 2 is equal to log base 3 of 9. The log base 3 of 9 is equal to 2. This means the same thing as written without the logarithm as 3 squared equals 9. This little equation is how I remember memorizing this definition in algebra way back in high school, which for me was like 1,000 years ago. See, the original equation in this example says that log base 3 of 9 equals 2, and I memorized sort of a arrow diagram for this. I memorized that the base always raised to whatever the logarithm equals, in this case the 9. The logarithm always equals the exponent. Logarithm always equals the exponent that I have to raise the base to get the thing I'm taking the log of. Sounds more complicated than it looks. So the statement from algebra that I originally made, that recall from algebra, it says that logarithm base a of y equals x. And if you think about the sort of arrow diagram, it means a raised to the x equals y. A raised to the x equals y, like 3 squared, 3 raised to the second power equals 9. Okay? All right. So now back to our problem. So end that little side trip. And back to our problem. We have in our problem x equals log base e of y. X equals log base e of y. And I want to solve for y. Not a problem. Not a problem. Just use the definition. That means e to, oops, my arrow turned out a little funny there. That means e raised to the, not better, not any better arrow here. E raised to the x equals y. So y equals e to the x. And this is the inverse. So if y equals log base e of x, then let's we were doing this in terms of inverses, so let me restate this again. Let's see, get rid of that. So if f of x, this is better, equals log base e of x, then f inverse of x equals e to the x. Or the best way to put this, if f of x equals ln, remember the log base e of x is ln of x, folks, I have a technical problem with my Surface. My computer froze for a bit. I may edit out that long pause. Or maybe I'll just resume recording. I think I'll just resume. So sorry about that. I'm curious to know what this glitch looked like. Okay. Okay. Technology. All right, so if f of x equals the natural log, and my pen still got really thick, log of x, then f inverse of x equals e to the x. This is the probably the most important thing early in this section. This is the definition of the inverse, or rather the natural exponential function e to the x. So I mentioned that the natural exponential function is often not called the natural exponential function. Sometimes it's just referred to the exponential function. Other times it's just referred to as e to the x. So e to the x is the inverse of ln x. So with that in mind, let's take a look at a couple of properties that should be satisfied by this function e to the x. So think about this if you can tell me. What is the natural log of e to the x? What is the natural log of e to the x? Think about it for a second. The natural log of e to the x. There are a couple ways to pathways to get to the answer here. The best is, right now, is that the natural logarithm is the function, and the exponential function e to the x is the inverse. And what do functions and inverses do to each other? I'm sure you were thinking this. They cancel each other out. So this is just x. Okay. So let me write a different way. So what is e, and then raised to the natural log of x? Well, this is just saying essentially the same thing. The exponential function and logarithm functions are inverses of one another. So however you compose them, either logarithm first, then exponential second, or vice versa, they cancel each other out. This is a very, very important set of identities. These two identities, they allow us to eliminate natural logarithms or exponentials. If you want to eliminate an exponential, you take the natural logarithm. If you want to get rid of a natural logarithm, you raise e to whatever the quantity is. Exponentials and logarithms cancel each other out because they're inverses of one another. Okay, so let's take a look at the graph of the natural exponential function e to the x. Let's approach this from the point of view of reflecting the natural logarithm function about the line y equals x. Remember, when you have a function and an inverse, and you graph them on the same set of axes, they should appear to be reflections of one another across the line y equals x. So we learned last time that the natural logarithm function looks like this. So it goes through 1, 0, grows very, 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 very slowly. The natural log of a large number is relatively small, even though that small can be made pretty big by taking the natural log of huge numbers, but generally logarithm of something large is relatively small. Okay, so keep that in mind as we go along. This is the graph of the function f of x equals the natural log of x. So here's the line y equals x. This little green line is what we're going to reflect the logarithm across to get our inverse. So the natural logarithm function goes through the point 1, 0. Just for emphasis, I'm going to put the comma 0 on there. It goes through the point 1, 0. So what's the corresponding point that the exponential function e to the x should go through? Remember, to find a point on the inverse, all you do is you switch x's and y's on the original function. So the inverse should go through the point 0, 1. 0, comma 1. Okay. So for the logarithm function, on the function f of x, let's see, as x approaches 0 from the right, y approaches negative infinity. That's a fancy way of saying that the logarithm function has a vertical asymptote. So what should be happening on the inverse? So on the inverse, we switch the roles of x and y. So y approaches 0 through positive numbers as x. I'm just switching x's and y. X approaches negative infinity. Okay, so that says that the graph of the inverse, at least to the left of the x-axis, should look like this. And that's sort of a reflection across ln x, partially across the line y equals x. So similarly, as x approaches infinity on the logarithm function, the y values approach infinity. Now remember, though, that the logarithm grows very, very slowly. So here's that statement again that I have about 2 inches above on the screen. The ln of large numbers is relatively small. So on the function, on f of x, if the x value is large, the y value is relatively small, even though the small values can be made very, very big eventually. So on the inverse, what does that mean? Remember, switch x's and y's. It only takes on the exponential function small values of x to produce very large values of y. So let's finish up the graph of this exponential function then. So the exponential function grows very quickly and very steeply. It only takes little x values, small x values, to get a very large y value. That second graph there, that's the graph of the exponential function, and it should be familiar to you. If it's not immediately, upon thinking about it for just a little bit, it should be. It's an exponential growth function, the same kind of exponential growth function that you studied in pre-calc and in Algebra 2. Okay, so the natural exponential function, the function e to the x, has a horizontal asymptote of y equals 0, the x-axis, just as the logarithm function has a vertical asymptote of x equals 0, which is the y-axis. Okay, and both of these graphs should be memorized. You should memorize the basic shape, basic properties. The exponential function grows, not slowly, it grows very, 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 very quickly. It takes only very small values on the exponential function to get very, very large, very, very large y values. Okay. Okay, so before we get into some calculus, let's take a look at some examples, some simple examples. These are examples from algebra. This is not a thorough review of logarithms and exponentials. It's just to get us familiar with the natural logarithm and natural exponential function. So let's for example, let's say solve A. Suppose you have an equation that says the natural log of x equals 7. And you want to solve for x. Okay. Now, how are we going to do that? Well, the logarithm function and the exponential functions are inverses of one another. So if we compose them together, they cancel each other out. Okay. So I'm going to take e to both sides. That's called exponentiating. That's called exponentiating. Exponentiating. That means taking e to both sides. More generally, it means taking some base to both sides, 2 to both sides, 3 to both sides. In this case, our base of our natural logarithm is e, so taking e to both sides, e and natural log are inverse functions. They cancel each other out. So x then equals e to the 7th. The calculator estimates that as about 1096.63. We'll say approximately. Okay. Let's see here. Okay. Okay, so example B. Suppose I want to solve something like the natural log of 1 plus x equals 3. Same thing. I want to get rid of or cancel out the natural logarithm, so I'm going to exponentiate. So e to the natural log of 1 plus x equals e cubed. E and ln are inverse functions, so they cancel each other out. So 1 plus x equals e cubed. Subtracting 1 from both sides, we get e cubed minus 1 for x. And this is approximately equal to, on my notes, I have 19.08 when I put it into the calculator. So approximately. Okay. Okay. Let's say, look at another example here. Let's do the kind of the opposite. Suppose I have something like e to the x equals 2. So if e to the x equals 2, this time I don't want to exponentiate. This is already an exponential equation. So I want to do the opposite. I want to take the natural logarithm of both sides. So I'm going to take the natural logarithm of e to the x equals the natural logarithm of 2. Natural log and e to the x are inverses, so however you compose them, they cancel each other out. Okay, so we get x equals natural log of 2. That's about 0.69. So this is approximately 0.693, say. Okay. All right. So let's look at another one. This one, I think this one is similar to something you're going to see on your homework. It's a little more difficult. So let's take a look at something like e to the 2x plus 2e to the x minus 15 equals 0. This kind of problem is usually done incorrectly by a whole lot of students. So I'm going to show you what's typically done incorrectly, and then we'll avoid that. So it's wrong. It's not correct to do this. To do, say, e to the 2x plus 2e to the 1x equals 15. Well, that's not necessarily wrong, but it doesn't get us anywhere. It's very common then for students to think, okay, then I'll just take the natural log of both sides, because natural logs and exponentials cancel each other out. But there's nowhere to go from here. You can't distribute the logarithm into addition or subtraction. It just doesn't work. It just doesn't work. So nowhere to go from here. Nowhere to go from here. Absolutely nowhere to go from here. So here's the correct thing to do. The correct thing to do is notice that this is sort of like a quadratic equation. Take a look at the equation again. It's e to the 2x plus 2e to the 1x minus 15 equals 0. And I can factor this. I can factor this into e to the x times e to the x And note that e to the x times e to the x is not e to the x squared. It's not e to the x squared. When you multiply expressions together, like e to the x times e to the x, the base is the same. You don't multiply the bases. You add the bases. So this is e to the 2x. Okay, so this does work out. So back to our problem: e to the x times e to the x, 5 times 3. Of course, I made things work out real nice for our example. Plus and minus will work out. And if you check out the actual multiplication, multiply through by the FOIL method or whatever, it works out. If you multiply the first two, you get e to the 2x. Outside, you get negative e to the 3, negative 3e to the x, plus inside 5e to the x, that's 2e to the x. And the last two, of course, give you negative 15. 5 times negative 3 is negative 15. So proceed as though it was a quadratic. So e to the x plus 5 equals 0. That means e to the x equals negative 5. Now think about that equation for a second. E it's a number. It's a strange number. It's like 2.72 approximately, but it's some positive number. You can't take a positive number, e, raise it to something, no matter what real number you're raising it to. You can't take e to a real number and get something negative. This is impossible. This is impossible. Okay, another way to think about this impossible is the graph of the exponential function. That's e to the x. It's sloppy e to the x, but it's e to the x. E to the x, positive. Always positive. The graph lies always above the x-axis, so it's impossible for e to the x to suddenly bend down and hit y equals negative 5. So that portion of the equation has no solution. So take a look at the second part. E to the x minus 3 equals 0. So e to the x equals 3. That one's all right. Take the natural logarithm of both sides. Now you can do it. Take the natural logs. So x is equal to the natural log of 3. Now just leave it as an exact value. X equals natural log of 3. Put in your calculator, get an estimate of it, whatever. So, okay. Let's look at one more graph before we get to some calculus. We'll look at some calculus, but I want to consider now another popular function. Consider, let's say, f of x equals e to the negative x. E to the negative x. This is also an exponential function. It's an exponential function, but it looks different from e to the positive x. So remember, let's take a little trip back to pre-calc. Recall from pre-calc that f of x and f of negative x are reflections about what? They're reflections not about the x-axis, they're reflections about the y-axis. So back to our course. E to the x and e to the negative x are reflections about the y-axis. The y-axis. This is important. This little example is a very important example in the sciences. So here's e to the x, y equals e to the x. If I reflect this graph across the y-axis, I get e to the negative x. So e to the negative x. They both go through the point 0, 1. And And you ought to memorize both graphs. These graphs happen over and over and over and over in STEM field mathematics, okay? Let's take a look at some calculus. Let's do some calculus. Okay. Well, before we get to even the most basic differentiation, let's take a look at a limit or two with exponential functions. So example, evaluate the limit. And the limit is going to be this one. So the limit as x approaches positive infinity of e to the x plus e to the negative x over e to the x minus e to the negative x. In engineering, this is an important function. You don't have to worry too much about remembering it as that special function, but it's actually called the hyperbolic cotangent function. Not to worry right now. Let's just think about it as this weird fractional expression with natural exponential functions. So let's take the limit of this function. We know some stuff about the natural logarithm, the natural exponential function, e to the x. We know that the limit as x approaches infinity of e to the x is positive infinity. There's, look at the graph. In fact, remember, the exponential function grows very quickly. Not only does it go to positive infinity, it goes to positive infinity very, very quickly. From our graph also of the second function, e to the minus x, we know that the limit of e to the negative x is 0. Okay. I'll indicate this with a little arrow. E to the negative x approaches 0 as x approaches negative infinity. E to the negative x has a horizontal asymptote as x approaches negative infinity. Okay, so with that in mind, you might want to go ahead and try to take the limit of this function. Well, equals e to the x goes to infinity, e to the minus x goes to 0, e to the x goes to infinity, e to the minus x goes to 0. We get infinity over infinity, and then that's not a number. Okay. You could probably get this to equal 1 using a little bit of logic, but let's stick with getting this limit using algebra. Now, we're going to go back to Calc 1 for a bit. In Calc 1, recall, in Calc 1, when we were finding horizontal asymptotes, that means we let x go to infinity and negative infinity. You'll be doing this stuff on homework. You'll be graphing functions again, using horizontal asymptotes, vertical asymptotes, concavity, all that good stuff on homework and stuff. Don't avoid those problems. I very commonly put them on tests. Okay. So back to our work. If we were evaluating this limit in Calc 1 that is looking for a horizontal asymptote of this function, we would take limit as x approaches infinity and separately negative infinity. The point is, if we were taking the limit of this rational function, we would divide numerator and denominator by the highest power in the denominator. What we would do is we would divide the numerator by x squared and the denominator by x squared, and then get something really nice. Close to infinity. If I distribute the 1 over x squared on top, I get 1 minus 1 over x. You can always pause the video and verify this if you're not sure. If you distribute the 1 over x squared in the denominator, you get 1 plus 1 over x, and then you get the point of dividing top and bottom by x squared. The point is that those 1 over x's, they approach 0. As x gets large, the reciprocal of x, 1 over x, goes to 0. And we get our limit. This limit then is 1 minus 0 over 1 plus 0, which is 1. Okay, now to our problem. Let's take the limit as x approaches infinity of our problem. e to the x plus e to the minus x over e to the x minus e to the minus x. Well, there's no highest power, but there's something that grows the fastest, and that's e to the x. So I'm going to use that same idea from Calc 1. I'm going to divide numerator and denominator by the fastest growing function. E to the x is growing the fastest. In fact, e to the minus x isn't even growing, it's decreasing. So if I take a numerator and denominator and divide by e to the x, I get the limit as x approaches infinity, distribute the 1 over e to the x, minus, now we have e to the minus x over e to the x. 1 minus e to the minus x over e to the x. This is, what do we do with those exponents when we divide? When you divide two quantities with the same bases, you subtract the exponents. If you don't remember that, you can also think about it as 1 minus e to the minus x, and then bring the e to the x up. Okay, there's a whole bunch of different algebra you can use to get these things right. You can either subtract exponents, negative x take away x would be e to the minus 2x, or you could bring the e to the minus x, e to the x up in the numerator, in each expression in the numerator and denominator. In any case, you get 1 minus e to the minus 2x. You add the exponents. 1 minus, oops, I think my plus went to a minus. There we go. Numerator has plus e to the minus 2x. And it's over. So if you're not with me on its being over, let x go to infinity. So this is 1 plus e to the minus 2 times infinity. 1 minus e to the minus 2 times infinity. 1 plus negative 2 times infinity is negative infinity. 1 minus e to the minus infinity. E to the minus infinity is 0. This is 1 plus 0 over 1 minus 0, which is 1. So this limit has a value of 1. Okay. So let's move away from limits and get into derivatives. I want the derivative. I want the derivative of the exponential function. I want the derivative of e to the x. Okay, so let's talk about differentiation. Let's see here. Okay, so I want the derivative of e to the x. Well, I remember the derivative of natural logarithm x is 1 over x. Okay, that's kind of a big thing to recall. This was one of the most important things in the last section. So now I want the derivative of e to the x. So I'm looking for the derivative with respect to x of e to the x now. So let's see what we can figure that out. So let's do it. Let y equal e to the x. So I want y prime. So I'm going to get y prime. But I'm going to use the fact that I already know what the derivative of the logarithm of x is. So I'm going to change this equation to its logarithm form. Easiest way to do that, I think, is just take the log of both sides, natural log of both sides. If you take the natural log of both sides, you get ln y equals natural log of e to the x is just x. Now take the derivative of both sides with respect to x implicitly. So the derivative of ln y is 1 over y times the derivative of the inside y prime. That's implicit differentiation. The derivative of x is 1. So y prime, multiply both sides by y, equals y. The derivative of the function equals the original function. That's incredible. There's only one function in the whole universe that behaves that way. Imagine that. You take a function, you take its derivative, you get the original function back again. That's incredible. That means the slope of the tangent line to the graph is the same thing as the y value on the graph. That's amazing. So y prime, but what was y equal to? Y is equal to the original function, e to the x. So the bottom line is, I'm going to write it big, the derivative with respect to x of e to the x is e to the x again. That's amazing. It's the only function that behaves that way. We have functions that are close to that, like the sines and cosines. Eventually, when you take enough derivatives, you get back to the original trig function. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of that is negative cosine. And the derivative of that gives you back to sine. So if you take 4 derivatives, you get back. 4 derivatives or 3 derivatives? If you take 3 derivatives, you get back to sine again. Okay. But this one, you don't need 3 derivatives. The exponential function, derivative of an exponential function is back to the exponential function on the first shot. So example, find y prime. Find y prime. A. Y equals e to the 7x. We'll keep it kind of basic. So the derivative of e to the x is e to the x. So what's the derivative of e to the 7x? Well, by the chain rule, the derivative of e to the 7x should be the derivative of the outside function, e to the x. Stays the same. It's e to the 7x times the derivative of the inside function. So this is 7e to the 7x. Okay, so let's try another one. Instead of making the exponential or the exponent a linear function, let's say x squared minus 3x. Now let's make the exponent a quadratic. So the derivative of e to something is that same thing back. That's the amazing thing about the exponential function. Or one amazing thing. But then the chain rule says we have to multiply by the derivative of the inside function. So we multiply by 2x minus 3. That's fine, or you could clean it up a little bit. We could write 2x minus 3 e to the x squared minus 3x. Okay, so I'm keeping it kind of simple. Let's see, let's do one more. What about y equals e to the 2x times cosine of x? So how are we going to take the derivative of this function? Well, we're looking at the product of 2 functions, so that's your big hint. So let's use the product rule. So y prime equals the derivative of the first function. The first function is e to the 2x. So the derivative of e to the 2 anything is that same thing back. The chain rule says I have to multiply by the derivative of the inside. So derivative of the first and then times the second function left alone. Plus the first function left alone, e to the 2x, times the derivative of the second function. Derivative of cosine is negative sine. Okay, I can do a little bit with this algebraically. I can factor out to e to the 2x times 2 cosine x minus sine x. So those are basic examples of differentiation. Let's look at the other big process, integration. So we know that the derivative with respect to x of e to the x is e to the x. So what's the antiderivative, the most general antiderivative of e to the x with respect to x? Well, it's got to be the same thing again. If the derivative of e to the x is e to the x, and go backwards, the antiderivative of e to the x should be e to the x again, plus a constant. It's amazing. The antiderivative of the function is basically the original function, maybe translated up or down by a constant. Example. Evaluate. Evaluate. I want to do some integrals. We're going to be doing a lot of integrals in the upcoming sections. Lots and lots and lots of them. So this is just sort of a beginning. So I want the most general antiderivative. I want the integral of e to the 7x. I can make a little u substitution here. A little u substitution. So let's say let u equal 7x, du equals 7 dx. So dx equals 1/7 du. Then substitute that into my integral. This becomes e to the u, and dx is 1/7 du. Constants can be factored from integration. Okay. And the integral of e to the u with respect to u is e to the u. That's a constant. So we finally substitute the 7x back in. Okay. Let's up the game a little bit. Let's take a look at, let's say, secant squared x times e to the tangent of x. I mentioned in the last video, trig is going to come back in a big way in this course, so we might as well start infusing it into our problems more and more. Well, we don't have many techniques of integration. You only basically have one from Calc 1 so far. We'll be getting lots more techniques. Right now, we just have basically u substitution. So if I let u equal tangent, then du equals secant squared. I have to remember our derivatives. So this integral is set up pretty nicely. So secant squared of x dx is du. So I'm looking at e to the tangent is e to the u. Secant squared x dx is du. I'm keeping it very simple, very basic for these first problems. And the antiderivative of e to the u is e to the u plus a constant. Remember that. U is tangent. So we get our result. Let's up things even a little more. Let's take a look at, say, the integral of e to the x over e to the x plus 1 with respect to x. This one's a little rougher for us. How can I do this? How can I do this? I basically, from this semester, I have two things. I have a couple of things. I have that the integral of 1 over u du equals the natural log of the absolute value of u plus the constant. And I have the integral of e to the x, we'll put u in there, e to the u du is e to the u again plus a constant. So this is what I got to work with. Your hint is that we need to use both. Okay, so how are we going to use the integral of 1 over u? Well, we do that by making the substitution. Let u equal what? Well, there's not much of a choice here. If we let u equal e to the x plus 1, then du is, well, what's the derivative of e to the x? It's the simplest derivative in the world. It's e to the x again, derivative of 1 is 0. So our integral transforms into over u, and e to the x dx, e to the x dx, what is that? What is e to the x dx? It is exactly du. Okay, so this becomes the natural log of the absolute value of u plus a constant. U was e to the x plus 1. And I want to ask you, I want you to think about this for a second. Can I do anything else with this? Can I distribute the logarithm? hoping you were thinking, what do you think I hope you were thinking? No, you can't distribute logarithms inside of addition or subtraction. However, something's happening here that happened in the last video. E to the x is always positive, always positive. So you're taking the log of e to the x plus 1. If e to the x is always positive, e to the x plus 1 is even more positive. So e to the x plus 1 is already positive. There's no need for the absolute values. And I'll make the same statement I made about absolute values on the last video. Try to get used to eliminating them when you don't need them and keeping them if you do. But if you, on your exams, you were to leave the absolutes, I wouldn't take off any points for it. Okay, just try to be efficient with your absolute values. You're very likely to get instructors that are not so lenient as I am in the future with that. So they may take off points if you keep them on when you don't need them. So here's our last problem. I want the integral of very similar looking function. I want the integral of the reciprocal of the last function, e to the x plus 1 over e to the x. You can't make the same u substitution. You would have u on top, but du on the bottom. You can't have that. So what are your impressions right now? If you're following along and you're really looking at this and not just viewing this passively, what do you think I should do here with this? What can I do? Well, what we could do is we could separate this into two integrals. We could separate this, or we could separate the function into the sum of two functions, e to the x over e to the x. We could not do this with the previous example. And 1 over e to the x. This is legit. This is perfectly fine. Okay, so now really we're just integrating 1 plus 1 over e to the x is e to the negative x. Okay, so this is the antiderivative of 1 is x. What about e to the minus x? Well, let's take that out separately. Let's take that out separately. E to the minus x dx. Let's do a little u sub on it. U equals negative x. Du equals negative dx. Dx equals negative du. So this is e to the u. Negative x is u. Dx is negative du. This is negative e to the u du. Negatives factor out. Negative 1 factors out. And the integral of e to the u is e to the u plus constant minus e to the minus x plus a constant. So back to our problem. That tells me that the answer then is x, because the antiderivative of 1 is x plus a constant, minus e to the minus x plus a constant. Okay, and that takes us to the end of this section. A special note for you guys is, I mentioned this during the lecture, your homework, plan to spend quite a bit of time on this particular homework section. In this homework, for this section, you're going to be asked to do some graphing, and the graphing should take you quite a bit of time. The graphing will refer you back to an earlier part in the textbook where you systematically graphed in Calc 1 by figuring out domain, intercepts, symmetry, asymptotes, vertical and horizontal asymptotes, increasing, decreasing, maxes and mins, concavity, and points of inflection. All of that stuff is very important, and you're going to need to review that. So you don't have to go back to Calc 1 problems. You just do the problems that I'm going to assign in homework, and they will suggest that you look back at the steps from an earlier chapter. Okay, and that's it. Okay, so again, we just finished section 6.2 star, and I'm looking forward to talking with you all again soon.